Apologies. Bless you, Celine. Okay, so like I said, this table is very important for you, so I apologize for the video if you're going to be missing the last 23 slides, but all right. Okay. Linear functions of a random variable. If we let a and b be any constants and we let x be a random variable, then the new random variable L equal to a plus bx is called a linear function of x. Using more advanced mathematics, the following can be proved. So I'm not going to read this out to you. You can take a look at it. I do not believe you will have anything like this on your test as far as this proof goes down here. The most I could see them asking would be this, basically you needing to determine if something is a linear function of x. If this ends up being on a test, we will probably take a closer look at that, but go ahead and at least make note of it. Obviously it makes sense that you can have a linear form for some of our outputs and experiments and whatnot. Linear combinations of independent and random variables. Suppose we have two random variables, x sub 1 and x sub 2. This will end up being in your homework. These variables are independent if any event involving x sub 1 by itself is independent of the following event x sub 2 by itself. Sometimes we want to combine independent random variables and examine the mean and standard deviation of the resulting combination. Let x sub 1 and x sub 2 be independent random variables and let b be any constants. Then the new random variable w equals a x sub 1 plus b x sub 2 is called a linear combination of x sub 1 and x sub 2. Don't worry so much about the words. Just basically pull away from this that when you see the w, which you will, and you're given basically two means and two y-intercepts, you will be able to go ahead and do regular adding and subtracting of them. It will make more sense when you do your homework. I don't know if anyone's done their homework yet, but if you have started it or looked at it, this will make more sense now. Using some more advanced mathematics, the following can be proved. So again, this is kind of showing you that you can do basic algebra with these ideas. Okay, so you can add and subtract means, you can add and subtract the variances, you can multiply them. Go through and work through the homework. I know it'll be a little difficult, but it makes more sense after seeing this. All right. Let x sub 1 and x sub 2 be independent random variables with respective means. Mu sub 1 equal to 75, mu sub 2 equal to 50, and standard deviations equaling to 16 and 9 respectively. So we are going to shove in everything that they give us. Here we're given an L is equal to 3 plus 2x sub 1. So then the mean of L would be using the mean of 1. So you end up with 1,024. And then they also show you using the manipulating the sigma. So you get 32. Notice that the variance and standard deviation of the linear function are influenced only by the coefficient of x sub 1. Why can't I see that? Come on, move away. In the linear function, okay? Again, this will make way more sense to you when you're going through your homework. All right. Here's an example of one that we are adding. Again, pay attention to what they're giving you. If they're telling you that they want the sigma squared, then you square both sigmas and add them together. Okay? Whatever they tell you to do, Just follow through and do it. I know it might seem intuitively weird to you at first, but that's literally all you have to do. Right? Questions on this approach? All right. I can tell you that peers in your past where we have done homework together in class, this has been one of the things where once they saw what they had to do, it made more sense to them. But before seeing it, it just wasn't something that they thought they were allowed to do. You are allowed to do that. Definitely let me know on the quiz if you need more attempts because of this. These are just examples. You can come back and watch the video if you really want to work through them, but you have homework you can do as well. All right, you can definitely write this one down. I'll give you a few seconds, few minutes to do that. If this is, you only really need one example, so we'll just go ahead and use this one. Any questions while those who like written notes are writing that down? Let's move on to Celine. Are you okay, or do you need a few more minutes?
Okay.
You're good? Okay. Let's go ahead and switch over to 5.2. All right. Binomial probabilities. So we'll definitely be able to get through 5.2. I cannot tell you if we will get through 3 or 4 today. We will probably do 3 and 4 on Wednesday, and then move on to chapter 6 on Monday. Okay, focus points. List the defining features of a binomial experiment. Compute binomial probabilities using the formula P of R equals C sub NR, P to the R, and Q to the N minus R. Okay, so all of this should look somewhat familiar to you. Use the binomial table to find P of R and use the binomial probability distribution to solve real world applications. This table can be a bit of a bear, so I'm not sure if any of you are able to go somewhere to print. If you can print, I would highly recommend getting a printed copy of this. If you bought the physical textbook instead of just the electronic or e-textbook, then this table should be in your textbook somewhere. I'm not sure what copies they gave you. I don't know if the school gave you physical or just the e-text, but I would recommend having a printed version of that. All right, binomial experiment. On a TV game show, each contestant has a try at a Wheel of Fortune. The Wheel of Fortune is a roulette wheel with 36 slots, one of which is gold. If the ball lands in the gold slot, the contestant wins $50,000. No other slot pays. What is the probability that the game show will have it to pay the fortune to 3 contestants out of 100? In this problem, the contestant and the game show sponsors are concerned about only 2 outcomes from the Wheel of Fortune. The ball lands on the gold or the ball does not land on the gold. Okay? So that's kind of what's in your mind right now. The problem is typical of an entire class of problems that are characterized by the feature that there are exactly 2 possible outcomes for each trial of interest. These problems are called binomial experience or Bernoulli experience after the Swiss mathematician Jacob Bernoulli, who studied them extensively in the late 1600s. Here are your reasons for the features of a binomial experiment. There must be a fixed number of trials. Okay, so that's your N, or your sample space, basically. The N trials are independent and repeated under identical conditions. So if you had the roulette wheel initially horizontal, and then you decided to make it like the Price is Right and flip it to being vertical, you cannot do that. It would be a completely different experiment. Each trial has only two outcomes, success denoted by S and failure denoted by F. For each individual trial, the probability of success is the same. We denote the probability of success by P and that of failure by Q. Since each trial results in either a success or a failure, then P plus Q equals 1, and Q or P can be found by taking the opposite from 1. The central problem of the binomial experiment is to find the probability of R successes out of N trials. Okay. If you would like some extra credit, you can try to come up with your own binomial or Bernoulli experiment. And if you can prove to me that why you feel it's a Bernoulli experiment, you will have to record on, I would recommend using Zoom. But regardless, you have to send me the recording and a write-up explaining, what your experiment was, why it was considered a Bernoulli experiment, and then actually show me some of the trials and then your data. You cannot go searching on the internet for something that's already been done. You can, of course, use the internet to kind of like get ideas of what exactly is a Bernoulli experiment. So, be as creative as you can possibly be. But obviously, I would recommend doing the extra credit after you've done your homework and quiz. Okay. All right, let's see how the Wheel of Fortune problem meets the criteria of a binomial experiment. We'll take their criteria one by one. So first off, we do have a number of trials because it wanted to know 100 participants, right? 100 contestants has the trial at the wheel, so then we have 100 trials. Assuming that the wheel is fair, the trials are independent since the result of one spin of the wheel has no effect on the others. Okay, so that's 2. We are interested in only 2 outcomes, if it lands on gold or if it doesn't. In general, the assignment of terms success and failure to outcomes does not imply good or bad results. These terms are assigned simply for user convenience. Okay, so far it's a yes. On each trial, the probability of success landing on the gold is 1 out of 36, which would mean that the other would be 35 out of 36. Okay. And we want to know the probability of 3 successes out of 100 trials. So in this example, it turns out that the probability of the quiz show will have to pay the fortune to 3 contestants out of 100 is about 2.3. Later in this section, we will see how this probability was computed. All right, so they're not going to show you how to do that just yet. They will probably show you next. All right, the central problem of a binomial experiment is finding the probability of R successes out of N trials. Now we will see how to find these probabilities. Suppose you are taking a timed final exam, which your exam will be timed-ish. I'm not going to give you over my workday. You have 3 multiple choice questions left to do. Each question has 4 suggested answers, and only 1 answer is correct. You have only 5 seconds left to do these 3 questions, so you decided to mark the questions on the answer sheet without even reading the questions. Don't do this, by the way. Don't do this. Assuming that your answers are randomly selected, what is the probability that you get 0, 1, 2, or all 3 questions correct? This is a binomial experiment. Each question can be thought of as a trial, so there are N trials or 3 trials. The possible outcomes on each trial are success S, indicating a correct response, or failure F, meaning a wrong answer. The trials are independent. The outcome of any trial does not affect the outcome of the others. What is the probability of success on any one question? Since you are guessing and there are 4 answers from which to select, the probability of a correct answer is 0.25. The probability of a wrong answer is 0.75. Now, if you took the SAT or if you're going to take the SAT, those are a little bit different because they're answer choices are 5. So you would have 0.2 and 0.8. Now that the possible outcomes in terms of success or failure of these 3 trials, let's use the notation SSF to mean success on the first question, success on the second, and failure on the third. There are 8 possible combinations of successes and failures, and they are written down here. By the way, if you have another situation like this, this will be the same sample pool. If you have 3 trials and you care about success and failure, these are your options no matter what the situation is. Okay, so you would not have to reinvent the wheel, for lack of a better term, and you could just come straight to this sample pool and pull it out. To compute the probability of each outcome, we can use the multiplication law because the trials are independent. For instance, the probability of successes on the first 2 questions and failure on the last is, so we have a probability of success times probability of success times probability of failure, or p squared times q. So then the probability of SSF is equal to roughly 0.047. Questions with how they came up with that? No? Good. Okay. In a similar fashion, we can compute the probability of each of the 8 outcomes. These are shown in table 5.8, along with the number of successes R associated with each outcome. Okay, so here's this nice little table. Again, if you have a physical copy of your book, it's easier to look at. If you do not, if you have an iPad or some other kind of e-reader, then you may want to pull your textbook up on the e-reader while you're working through your homework so you can have a reference. All right, good with that? Cool. Now we can compute the probability of R successes out of 3 trials for 0, 1, 2, or 3. Let's compute P of 1. The notation P of 1 stands for the probability of 1 success. So at least 1 success. 1 success, it can be either the first, second, or third, but you have to have 1 success. So then we're looking at the following. Here they kind of broken it down for you, and you end up getting 0.422. All right. Okay. Here we have another table. It basically just shows up that same kind of breakdown. These should add up to 1. I believe they will. 0.422 plus 0.422 plus 0.1 plus 0.016. Yes. So 1.001, which if you round is just 1. Why do you think the first and second are equal to each other? I think it may be just a coincidence in this case, but I do think it's rather interesting how these are all kind of found out. And again, if you have a similar thing on your homework, this doesn't change. The only thing that changes would be the probabilities that you would be given. So you can go straight to here if you have a similar situation. Okay. All right. Formula for the binomial probability distribution. You want to pay attention to this. Okay. It's broken down for you. Go ahead and take a look. Write it down if you are a writer. Snippet it if you are not a writer. Come back to it later if you are someone that likes to do that. So probability of R, we're going to take n factorial, which I would ask you what that means, but it tells you at the bottom, so I'm not going to waste anyone's time. Little p is equal to the probability of success on each trial. Q is equal to the probability of failure on each trial, which you find doing 1 minus p. R is equal to the random variable representing the number of successes out of n trials. So R will always be less than or equal to n. All right. So if you're given the information and you have to plug it in, never take the bigger number to be R. All right. Is this making sense? The R will always be less than or equal to the n. The exclamation point is called your factorial notation. We already discussed it in chapter 4. And so if n would be 3, then it would be 3 times 2 times 1. Okay. There are two special cases. 1 factorial is equal to 1. 0 factorial is equal to 1. All right. C n sub n r, it basically means C for choose R out of n. And there's your formula for it. Again, we discussed this already. All right. Okay. This is just working through that problem set. So, or that formula. Privacy is a concern for many users on the internet. One survey showed 59% of internet users are somewhat concerned about confidentiality of their email. Based on this information, what is the probability of that for a random sample of 10 internet users, 6 are concerned about the privacy of their email? Let me tell you, that is an age thing as well. When I was younger, I could have given 2 junks if someone had my email. I didn't care. I will tell you now that I am old, I absolutely hate getting junk mail. It takes up so much of my day. I hate when people have my email. All right. And I used to think, oh, well, it's okay because I have a junk email. No, it doesn't matter anymore. I don't like them having any of my emails. This is a binomial experiment with 10 trials. If we assign the success of internet user being concerned about the privacy of email as 59%, we are interested in the probability of 6 successes. So we have n equal to 10, p equal to 0.59. How did they find their Q? I didn't read 41% anywhere, so how did they find their Q?
They subtracted p from r.
Close. P minus 1. But yes. Okay. They followed the chart. All right. And then R is equal to 6 because that's the number of successes. So they plug everything in where it belongs. I highly recommend, I cannot express with more recommendation that you do this. Okay. If you do this, it will help doing this much easier. All right. Plus, on top of that, if you do that, I can then see where your mistake is. All right. Why can't I see this in full screen anymore? That's annoying to me. Okay, fixed it. So there's a 25% chance that exactly 6 out of 10 internet users are concerned about the privacy of email. Okay. I would guarantee you that if you broke that down and you cared about your age ranges of your participants, that percentage would go up the older the people are. All right, so here this is telling you use table 2 of appendix 2 or a calculator. Okay, I would just recommend using your calculator. All right. Many calculators have built-in combination functions on the TI-84, so that's just explaining to you how to use it. I'm okay if you also decide that you just want to Google it, like what is the combinations of 10, choose whatever. You can also just do the formula. That works as well. Questions on that? No? Okay. Using a binomial distribution table. Again, I don't recommend using the table, but if you need to use it or that is your preference, then I would suggest printing it out. So 4 or fewer successes, you're looking up in the table for that. It would be a bit of a chore to use the binomial distribution formula to compute all of the required probabilities. Table 3 of Appendix 2 gives us the probability values of P for R for selected P values and values of N through 20. To use the table, find the appropriate section for N and then use the entries in the columns headed by the P values and the rows headed by the R values. So here's an example of what it looks like. You literally go across and then also down, and where it intersects is the answer. Okay. It's not hard to use the table. If you're using it online in some kind of capacity, you may have a harder time with it. You may want to use it on an e-reader or print it out. Okay. Your prerogative, you can decide how you want to do it, but you find each of your probabilities and then you add them up. Okay. Since we have the complement of the event, then we can also take 1 minus and get the same thing. All right. Okay. A biologist is studying a new hybrid tomato. It is known that the seeds of this hybrid tomato have the probability of 0.70 of germinating. The biologist plants 6 seeds. What is the probability that exactly 4 seeds will germinate? Okay, so we have 6 trials. The success rate is 0.70, which means our Q will be 0.30. We plug everything in. They're using the table. Okay. Then we find the entry for the row headed P equals 0.7 and R equals 4. This entry is 0.324. So what is the probability that at least 4 seeds will germinate? Then they're going to do P of 4 plus P of 5 plus P of 6. So you get 0.745. Again, you will understand this more as you do your homework. Okay, all of that we've currently done is sampling basically with replacement. So when a participant or a contest person goes to spin the wheel, do we tell them, oh, you can spin the wheel, but the last person won the gold, so we have to remove it and it's now going to be silver? Do we do that? No. The wheel is the wheel no matter what. We don't replace things, move things around. It just is what it is. What we are about to look at next is sampling without replacement. So the best example I can give you for this is whenever you have to pull out a marble, normally we need to know if it's with replacement or without replacement. If it's with replacement, then if you pull out the marble, you write down what color it is, and then you put the marble back. You shake it up, and then you pull out a new marble. If it's without replacement, you pull the marble out, you note the color, and then you leave it on the table. And then you pull out a new marble. Okay? Do we get the difference? This is very important for you. Okay? If the population is relatively small and we draw samples without replacement, the assumption of the independent trials is not valid and we should not use the binomial distribution. The hypergeometric distribution is a probability distribution of random variable that has 2 outcomes when sampling is done without replacement. This is the distribution that is appropriate when the sample size is so small that sampling without replacement results in trials that are not even approximately independent. A discussion of the hypergeometric distribution can be found in Appendix 1. Okay, so that is that. We do have a little bit of time left, but the next 2 sections are just as long. So,